Hey everybody, welcome back. Uh, we're changing things up just a little bit this week. Okay, we're taking a break from the Jeppesen book, and we're going into chapter 12 of the Airplane Flying Handbook, and that link is down below, and it's probably all over Canvas too. The multi-engine training is part of the Jeppesen commercial syllabus. Um, but it's not included in the Jeppesen book that you have. It's a separate green Jeppesen book that you would buy, and then the syllabus refers to pages in that chapter, and then you go fly the multi-engine aircraft, obviously. But keep you from having to go down and buy yet another book for this course, we're going to use what's already been published for us on the FAA's website using the Airplane Flying Handbook. So today we're gonna take this video, maybe the next two videos, we'll see how it plays out, and talk about multi-engine aerodynamic terms, talk about some specific multi-engine systems, the aerodynamics, and specifically the engine out aerodynamics that will take a lot of your time when you're learning how to fly multi-engine aircraft. Now, the reason we cover this, once again, it's in your Jeppesen commercial syllabus. The objective with the multi-engine lesson is to become familiar with the regulations as they apply to multi-engine aircraft, describe normal operation, and then the next lesson, or next break in the video, or the next video will be engine out, or one engine inoperative procedures in a multi-engine aircraft. Again, chapter 12 of the Airplane Flying Handbook, when they talk about transitioning to multi-engine airplanes. And then sometimes I get some information from the Pilot's Handbook of Aeronautical Knowledge, also available, link down below, or you can see it right there on the page. You can search for it on the FAA's website too. There are some other references for this one. I should have put others in there. There's a few specific videos that help demonstrate what we're discussing, and some other websites, and those are obviously given credit when we get to them. So why would we want a multi-engine aircraft? I guess, one more reminder, if you haven't read chapter 12 of the Airplane Flying Handbook, go ahead and pause this video and go do that now, and then you can refer back to it during the video to answer some questions you might have. Why would we have more than one engine? Because we want to, because it looks cool, because you get to go faster. And then there is a safety aspect. With four engines, you still have three if one quits. However, it's not necessarily that cut and dry. If you have four engines, you've actually just quadrupled your chances for an engine failure. So I hope the other three are dependable, and I hope the other three make enough power to haul around that dead weight of that fourth engine. We will discuss some larger aircraft terms, V1, V2, takeoff safety speeds, balance field length, and accelerate and go distances. A lot of that's not really going to apply to you and your light twin aircraft, but so we'll talk about some of the terms, but I'm not expecting you all to get your type rating in an Airbus A380 from this video. So the goods are more power, more redundancy, and more performance. The bad is more complex systems. You have aerodynamic problems you got to worry about. You have other concerns. You burn a lot more fuel. You have a lot more things that can go wrong, basically. Now we've got a lot of terms to cover, and they pretty much will be in this video. And again, you can go look in the Airplane Flying Handbook or the PHAC. So, twin engine aircraft, they obviously can haul a lot more stuff around. So you want to go faster, farther, higher, then you're probably going to need more than one engine's worth of power there. So critical engine, we'll get into each one of these. This is not a page for me to get into them all necessarily, because each one of them I think has their own page. What I will point out here is in the airspeed indicator, you have a couple different lines here, and VMC is the red line that's shown here. Okay, so that is minimum controllable speed, and there's a whole bunch of criteria in how that's determined, so we're going to definitely talk about that for a little while. It's on here because that's a bad thing. One engine quits, you do not want to go slower than that speed whatsoever. The other new change to our airspeed indicator is VYSC. That's the blue line here. When you guys start flying multi-engine aircraft, you're going to probably hear blue line, blue line, blue line, probably 100 times until you start hearing that voice without anybody else saying it. And then everything else is the same. Your VSO, VS1, VFE, VNO, VNE. So your two additional markings on the instrument there are VMC and VYSC. VYSC is VY, just like on a single engine aircraft. It's the best rate of climb speed, but it's VYSC, and that's your best rate of climb with one engine inoperative. So if you can climb, you need to climb at that airspeed. You will get the best rate of climb. If you can't maintain altitude, VYSC will make you descend at the slowest rate. Let's say if you're flying at a high altitude and one engine quits, the other engine doesn't make enough power to keep you that high anymore. VYSC, or blue line, will be the speed that keeps you in the air the longest. And there's also normally a lack of glide speeds, because if you lose more than one engine in a multi-engine aircraft, you're probably a test pilot, and probably shame on you, but not necessarily. Okay, Cactus 1549, it wasn't any fault of the pilots where they had a dual engine failure and they kind of had to make it up as they went, right? So that was a Miracle on the Hudson, in case you have no idea what Cactus 1549 is. Okay, so VXSE, best angle of climb speed with one engine operative. I really hope you never have to use that, because it's closer to the red line than you would like it. But if the other alternative is hitting a mountain or a tree, then you want to know what your VXSE speed is. And then VYSE, once again, is important enough we need to talk about it. It is the blue radial line and is the best rate of climb speed with one engine inoperative. Normally, you'll hear me a lot of times, I'll say engine out, or I'll say one engine or single engine. And that is because you're going to learn how to fly a twin engine. So we always talk about having two engines and always losing one. But you would still have one or more engine out air speeds, performance numbers, and charts. B-52 has 8 engines, so they have multiple procedures. What if they lose more than one? And VSSE is not one that's shown on the airspeed indicator, and that's something your MEI, your multi-engine instructor, needs to know. That is a safe intentional one-engine inoperative speed. They used to be called something different. So basically, that is the slowest speed I can simulate an engine failure on you. So it's good for you to know that, because if an engine failure happens below VSSE, I didn't do it. It's real. And if your instructor does simulate an engine failure below VSSE, you can get a new instructor. The one exception being takeoff engine simulated failures, because obviously you're still on the ground, you're not in the air yet. VMC, okay, so this is not the only time we're going to talk about VMC. That's our red radial line right here, okay? And these are straight out of one of your textbooks. I think it's the AFH. This is the minimum speed at which directional control can be maintained under very specific set of circumstances, and we'll talk about Part 23, and we'll talk about some other certifications for requirements for it. So basically what they did was they put the aircraft in the worst possible condition, the worst CG, gross weight, flap setting, gear setting, the critical engine being inoperative. That's the one that hurts your performance the most. And they basically, under the worst set of circumstances, VMC is that red radial line. Anything slower than that, you will lose, or you could lose, directional control or roll control. You will run out of aileron and the aircraft will still keep banking in that direction, or you will run out of pedal and the aircraft will keep yawing in that direction. So long as you maintain above red line, in theory, you're going to maintain control of your aircraft. You're not going to lose it. Yeah, it still does what you want it to. But if you go below that red line, below VMC, no matter what you do with your ailerons and your rudders, it's going to keep going where it wants to go. So you've lost the fight at that point in time. You will never do this, but you do have to demonstrate a VMC demo on your check ride, and so you will actually practice bringing it right to VMC, or minimum controllable speed. And then once you recognize that you have now lost your directional or your aileron control, then you go through the steps, which is basically pull the power off of the operating engine, gain airspeed, and then start adding power back in again. There's a whole bunch of criteria to it. You got to maintain your heading within 20 degrees, up to 5 degrees of bank, and that is towards the good engine. You raise the dead engine, and there's pounds of pressure on rudder pedals. And Part 23 got pretty crazy on it, on certifying this. So how's that apply to you? Well, you're going to hear us a lot of times talk about a light twin. So when I mean a light twin, we mean a multi-engine aircraft less than 6,000 pounds. So your Beech Duchess or your Seneca or less than 6,000 pound aircraft and or a stall speed less than 61 knots, then you're in a light twin. Probably the ones you're going to learn how to fly once again, and the twins. Now, if you're in a big aircraft, so let's start with that. You're in a big multi-engine aircraft, more than 6,000 pound, and or a stall speed greater than 61 knots. They have to determine what their climb rate will be at 5,000 feet MSL if one engine of the two engines fail, or one engine of the more than two engines fail, and they must maintain a 1.5% climb gradient. That's half the steepness of a glide slope. It's not not a very good climb rate, but the point is that it is a positive climb rate. So if you're in a heavy aircraft and you lose one engine, if you're at 5,000 feet MSL or lower, you're required to be able to maintain a climb gradient. That's a totally different story for a light twin. So if you're less than 6,000 pounds, again, like the Duchess here, all they have to do is determine the climb rate. The climb rate of 5,000 MSL must be determined. There is absolutely no requirement that it be a positive climb gradient. If you fully load this aircraft to its max gross weight and lose an engine at 5,000 feet, it will be descending, not climbing. So just because you have two engines doesn't mean that you can go wherever you want if one engine fails. It depends how high, hot, and heavy and humid things are. And then obviously what you do with it when it happens. So why else do we want a twin engine aircraft? Well, back when jets were fairly new, all the long haul aircraft all had four engines or three engines. The DC-10s, the MD-11s, the L-1011s, and I could do this all day. And then, of course, the queen of the skies, the 747, had four engines. It had four engines because it's going to carry a whole lot more with all four, and that way if one quit, it would still have three to get it across the ocean. Well, having three engines when you could just have two is a waste of money and weight. So we have a lot of twin engine aircraft that are now ETOPS certified. And you see here's the nose of a 737, obviously. And you'll usually see ETOPS marked on the nose gear door of aircraft that are specifically allowed to do extended twin engine operations. So it is not just there's a lot that goes into ETOPS designation. It's how reliable the engines are. It is how far away from land they are. It is different types of fire extinguishers that are installed. There are so many differences that makes an aircraft ETOPS. The point is, not every jet that has two engines is ETOPS. And what has happened is an air carrier landed an aircraft, I think in Hawaii somewhere, and then as they taxied in, realized that it wasn't an ETOPS aircraft. The wrong aircraft got assigned to that flight that it shouldn't have been, and they ended up landing somewhere else, and then they weren't allowed to fly back with passengers. They had to fly back a Part 91 flight. A 737 800 going across the ocean with no passengers in it, paying for the fuel, costs a lot of money. So ETOPS, the reason we do that is if we didn't have ETOPS, let's say if this airplane wasn't ETOPS, then you would have to go around your way so you could always be within a certain time of an alternate airport. And the ETOPS certification will give like 120 minutes or 180 minutes, something like that. So if you're ETOPS certified, you can go direct between locations or at least farther away from gliding spots or from alternate landing spots. Until aircraft became more dependable, they had to go out of their way. They had to go through the North Atlantic so they could go through multiple alternate landing spots. But yeah, so ETOPS is a pretty cool thing to have, and it's a term that you're going to want to know if you want to stay in this business. And here's a nice article about the 737 Next Gen. ETOPS went from 120 to 180 minutes, and the article on the FAA's website talks about, or on Boeing's website here, mentions all the hoops they had to jump through to make that happen, and this let their air carriers actually save themselves a lot of money because, again, they got to go directly from destination to arrival without having to go out of the way to stay near alternates. All right, let's start getting into literal systems. So we hit on some of the terms. You can find the other terms in the book, and the other ones will probably come up as we get there. So let's talk about some of the differences here. So the one big difference is a propeller in a multi-engine aircraft is going to be different than the propeller in a single-engine aircraft. You go out there to a single-engine aircraft to constant speed propellers, and generally what's going to happen is when the oil pressure leaves the propeller, like when you shut the engine down, the spring or nitrogen or other forces inside this propeller hub here drive it to its low pitch, high RPM position. That's best for takeoff and for landing. Well, you don't want that to happen in a multi-engine aircraft. If the engine quits or it loses oil pressure, you want that propeller to feather. So in a single-engine aircraft, the oil pressure is making it go to its high-pitch, low RPM position, and then it spring loads or air loads back to its low-pitch, high RPM position, like for takeoff and landing. In a multi-engine aircraft, and a full feathering multi-engine aircraft where that propeller goes a full 90 degrees from where it used to be, it minimizes the drag from that propeller. So there's a lot going to it. The biggest, most important difference here is that oil pressure keeps it from feathering. So if the engine quits or it loses all its engine oil, that propeller will feather. There are other ways in turbine aircraft, and some systems have auto feathering. Some aircraft have auto feather systems installed where it automatically feathers the propeller if there's an engine failure, and that causes other problems too. So the biggest difference in a single engine aircraft, the oil pressure increases pitch. On a multi-engine aircraft, oil pressure decreases pitch. Again, there are exceptions to every rule, but this is pretty general for the light twins you'll be flying. So there's going to be a link down below of the Macaulay Propeller System Technology Guide. It's the same one we talked about when we talked about constant speed propellers back a few videos ago in our single engine section. But you flip a couple pages and they talk about multi-engine aircraft and full feathering propellers. So here's there's no extra control from before. You have throttle, you have RPM, you have mixture, but in a feathering propeller, you move it full back and it actually feathers the propeller. It turns it to a full 90 degrees to minimize drag. Now, what's causing them to feather oftentimes are going to be nitrogen pressure inside the hub. There might be springs that preload pressure. There might be some counterweights that are twisting the propellers one way or the other. And then again, the only thing that keeps it from feathering is oil pressure. And some cool systems like the BE-76, the Beach Duchess, has an oil pressure accumulator. So it stores a little bit of oil pressure in the cylinder to help you unfeather the engine in flight. Because yes, now that you're flying multi-engine aircraft, you will shut down an engine in flight. Like straight up, mixture back, feather the propeller. It's going to be nice and cold, and then you got to get it started again in the air. You got to do that on your check ride. It's awesome to be able to actually shut an aircraft engine off in flight on purpose and have fun with it. Now, if you go out there in the flight line, though, and you see all these light twin aircraft and their engines, their propellers are not all feathered when they're sitting there, and that's because there's a centrifugally operated pin that's inside the hub that keeps it from feathering. So here's out of the POH for the Beach 76, a feathering lock operated by centrifugal force. So around 800 RPM or so, these locks get slung out because of centrifugal force and then allow the thing to propeller. What happens is it prevents unintentional feathering. So every time you shut down, it doesn't fully feather the propeller because then it's a whole lot harder to get it started again. Now, the biggest exception to this rule is a turbine engine. Most turbine aircraft, whether it's a single engine or a twin, will fully feather the propeller when it shuts down. Okay, so I'm talking about light twins generally don't feather when they're shut down. If you see it's feathered, somebody did something wrong or something's broken. And then it also says if for any reason that you have to make sure that you feather it before the engine drops below 800 RPM. And in normal flight conditions, if you lose an engine and maintain your VYSE speed, the engine will still be windmilling out there. And it'll probably be windmilling higher than 800 RPM. Actually, when the engine quits, you really don't know because it looks and sounds like it's still running, and the tachometer still says it's still at a high RPM. And then, so we'll talk about other steps and figure out how to identify a bad engine later on. So again, why do we need to feather a propeller? Well, the change in drag being created by that propeller goes down tremendously by feathering that propeller. So at a flat blade position, you have the most amount of pairside drag. All right, it's not just the propeller that's causing drag; it's that 6 or more foot diameter disc that's all creating drag. So it's not just the propeller causing drag; it's the entire propeller disc that's creating drag as it windmills. So stopping the propeller makes a lot less drag. So here's a few things. Here's a P3 Orion with a feathered number 1 engine over here, for instance. And here's kind of a close-up of the hub. And inside here is spring pressure. Sometimes there's nitrogen pressure. And sometimes you see counterweights installed on these controllable pitch propellers too. So there's aerodynamic twisting forces. So just the air hitting on the propeller blade tends to drive it to its low pitch, high RPM position. But we don't want that. Remember, we want this propeller to feather if the engine quits and the oil pressure, it loses oil pressure. So you see some aircraft will have these counterweights installed on there. There's usually 1 counterweight per propeller. And it's pretty cool how it's geared inside of here. I don't need to get into the weeds on this, but the counterweights try to drive it to its high pitch or its feathering position, its low RPM pitch. So if you see counterweights, that's what they're for, is to help, is to offset the aerodynamic twisting forces on those blades. A little diagram on how those counterweights work. And then, so we, in the past, had already talked about, you got your piston, you got your oil moving back and forth. The oil comes in being directed by the pilot valve and the governor, and oil moves the piston. The piston's connected to each propeller, and all propellers change the same amount. And so what do we have? We have the hydraulic oil force, the aerodynamic force, and the nitrogen pressure or the spring pressure force, and the counterweights all fighting against each other, basically. And then this is a great breakdown of what makes the propeller want to do what. What you really need to know about this is that, how to fully feather a propeller. Okay, so in normal condition, if you will, it's got that small range, right, where it will adjust its pitch to maintain the desired RPM. And then when it's feathered, it's full 90 degrees from it. So you see the airflow won't hit the propeller and continue the disc to spin. And then, you know what? If we're going to be cool with this kind of stuff, we might as well put a reverse on here too. So you've got the beta range, and then you've got the reverse range too. Usually these are going to be reserved for very complex propellers and usually just turboprop aircraft, where you hear the change in sound when they're taxiing to when they start taxiing forward to stopping. And that's when they go to flat pitch. They make less thrust so they don't have to use as much brake. Or straight up reverse thrust. The engine doesn't stop and turn backwards after you land, but the propeller, what started, the positive blade angle coming into land, rotates back to a negative pitch. Now it's providing rearward thrust. That's reverse thrust. Now, another cool thing that we do on a lot of these light twin aircraft is we have counter-rotating propellers. Okay, so if we just had your normal 2 Cessna engines on here, then both engines would be rotating clockwise as viewed from behind. And then the left turning tendencies that you have before in your single engine aircraft would now be made more than twice as bad because you have 2 engines. I say more than twice as bad because you actually end up with a whole lot more left turning tendencies being created by the right engine because it's offset from the center line of the aircraft. So one thing that makes all these aerodynamic hazards a whole lot less dangerous and easier to handle is if we put on counter-rotating propellers. So instead of having them both rotate the same direction, you put a different engine with different propellers and different part numbers on there, and they rotate opposite directions. Now, for safety, usually you'll see them rotate this way. They go inwards as they go in from the top. So, as viewed from behind, this one would be clockwise. This one would be counterclockwise. And you see a lot of examples of, here's a PA-34 Seneca. You see where the anti-eye strip is on the blades. These both go that direction. Now, this adds to the complexity of the aircraft because now you have to have two different engines with two different part numbers and two different propellers. But what they do is they do this for safety, basically. And we'll talk about the critical engine and the PAST factors that make it critical. Also, while we're looking at this, we've got prop anti-ice, we've got windshield anti-ice, we've got vertical stabilizer anti-ice. They're a pretty sweet aircraft we're looking at right here. And this is still just a light twin. Here's the Beech Duchess. I actually did my ATP check ride in this exact aircraft. And it's kind of hard to see the propellers on that one, but it also has counter-rotating propellers. Now here is a Piper Aztec. It's a much older aircraft. This is much higher performance. All right, this has, each engine is 250 horsepower on this guy, as opposed to 180 horsepower on each. So it's way more powerful. This is 60 aircraft and over a 2,000 pound useful load. That's carrying almost 100 gallons of fuel, and it's awesome. It's got so much engine crammed into those tiny nacelles that you really got to be on top of using your cow flaps, as you can see right here. You really got to manage your fuel. It has 4 fuel tanks. It has 2 in each wing, and it has hydraulically actuated landing gear and hydraulic flaps, and it only has 1 physical hydraulic pump. It's not electro-hydraulic. And then it only has, I think, like 1 alternator on the other engine, and unless it's really upgraded with some stuff. So if you lose 1 engine, you're going to lose an engine and a hydraulic pump for your landing gear and your flaps. If you lose the other engine, you're going to lose the engine and the alternator. So you're going to lose something besides just a whole bunch of power. But one of the points I'm looking at here is these are not counter-rotating propellers. So this engine is more expensive, it's bigger, it's more powerful, and it would have cost a whole lot more to make a special engine just for this one airplane that would go counter-rotating. You go out and look at pretty much any multi-engine turboprop aircraft or very high-performance piston aircraft, and they do not have counter-rotating propellers. Especially in turbine aircraft, those engines are so reliable that it's much less likely to happen. But it's just the complexity of having so many parts that need to spin the other direction that keeps us from doing that all the time. Okay, some other system stuff while we're talking about it. You've heard a multi-engine fly over, and it doesn't just sound like 2 airplanes. You'll hear the sound between the 2 engines basically fighting for your attention as they fly over. And it's even worse in the aircraft. Usually, if you guys have flown like a commuter, a twin engine turboprop, or usually a smaller airplane in places, so a lot of you have flown in multi-engine turbine aircraft at least, and during takeoff and landing, we just want as much RPM as we can get because we want as much power as we can get, and we kind of forego the slight adjustment of RPM on one engine versus the other. But once we're climbing and cruising, that drumming sound, the wow, 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 it puts you to sleep pretty quick. And I tell you what, there's fewer things that get under the skin of a multi-engine instructor than that. So how to sync the props to where they're the same RPM so they don't make that drumming noise anymore. They mesh. They just make the same sound. Well, you could have systems that do that, like the synchro phaser here, where you put it in auto and it has a one engine that sets the pace and the other one adjusts to match it, basically. You might see some synchronizers, synchrophasers, you might see some gauges. Honestly, the best way to do it is just by sound. You pull back slowly 1 propeller on 1 engine, and as they hit the same RPM, you will just hit that sweet spot. Most of these light twin aircraft don't have the complex phaser systems or anything like that, so you're just going to do it with yourself moving the prop control. And synchrophasing would be to put them out of phase from each other or into phase with each other. So here is, not an Osprey, because this is an Osprey, but the 609 civilian version of it. If both blades pass the fuselage at the exact same time, you're going to get a pressure wave off of both of them, as opposed to if they're out of phase from each other, it'd be a pressure wave on one side and then the other. And I really show the Osprey does not do that. You see, these things are specifically in phase with each other, and they stay that way. So yes, there's two engines, and both engines drive both propellers because there's a drive shaft that goes through the entire wing and connects them both. That way, if they have one engine failure, they still have both propellers that are being powered by the other one. And why don't they offset the phase on these things? Because when they have it down here for maintenance, if this is just a few degrees off, it wouldn't work. It wouldn't fit. They'd be hitting stuff on the ground. So, okay, let's keep going, talking about systems. The fuel system is going to be a little more complex in these aircraft. You have more engines burning more fuel. You got to have more places to put them. So this is a simple fuel injection system for a light twin recip engine aircraft. So if you just look at half of it, it's all the same. You got a fuel selector. You got one or more tanks. And then you've got some kind of a strainer, and you've got some kind of a fuel control. And it goes to the fuel manifold and goes down to your fuel injectors. Okay, so you double that, and now you've got a multi-engine fuel system. The one largest difference here is the ability to feed one engine from the other fuel tanks. We call that cross feed. So if, let's say, you have the left engine fail, it would actually might be a good idea to have the right engine burn the fuel out of the left wing to make the left wing lighter, because now you're hauling around a dead engine on it. So you have the ability to then burn fuel from where you want. And it totally, Cessnas, Pipers, Beech, they all have their own way of managing fuel. So you really do need to learn that fuel system for that aircraft. The Cessna twins are notorious for having somewhat complex fuel systems. So in the air is the wrong time to figure out if you know how to use it or not, if you know what I'm saying. So yeah. Now, fuel management, okay, it's going to be a lot of the same. So here's, it's not just as simple as the left, right, and both like in your single engine aircraft, okay? So you're going to have left main, right aux, right main, left aux. So you've got a whole lot of options here. You might be able to transfer fuel from one tank to another, or you have to just burn it in a certain order to keep your CG from going out of order, or weight on the wings. The Cherokee 6, it's a single engine Piper with a 300 horsepower engine on it. It has, I think, 6 fuel tanks if you have the tip tanks installed on it. And there's a certain order you have to burn them all in, but you can't pump fuel from one to the other. You can only burn fuel from it. Yes, anyway, so learn how to use the system for the aircraft that you're flying. It's so much more important now. And a boost pump is one way to transfer fuel. A boost pump might be required when you're cross-feeding. And when you're switching tanks, we'll turn the boost pump on, switch the tanks, turn the boost pump off. If the flow drops, then hurry up and go back. And just a couple terms we need to talk about: fuel exhaustion. Okay, that's when you exhausted your fuel. You ran out of it. You don't have any more fuel in the aircraft to give the engines. As opposed to fuel starvation, which means there's fuel in the aircraft, it's just not getting to the engine. And many times fuel starvation occurs because the pilot forgot to or mismanaged the fuel, and the engine was trying to take fuel out of a tank that didn't have any fuel in it any longer, but there was fuel in some other tank somewhere. Now, occasionally it's because of some kind of a fuel feed problem, like something clogged the tank vent, and there was fuel in the tank, and the pilot wanted to get it to the engine, but they couldn't because it's something mechanical. It does happen. Okay, another thing with these multi-engine aircraft, a lot of times you'll see a combustion heater. Here's the data plate for a Janitrol heater. So you read the POH for the Piper Aztec, they talk about the Janitrol heater. That's a combustion heater. It's usually inside the fuselage with you. And the reason we need a combustion heater is because the cabin, or I'm sorry, the reading cabin over here as I'm trying to talk, the heat exchanger heater like you had in your single engine piston aircraft, where the exhaust gets really hot and heats up air, and then you get that heated air. It doesn't work as well because the engine's not in front of you. The engine's out there on the wing, and then all that air has to go through tubing into the cabin where it would be cool by the time it gets to you. So not only that, but we've got all this extra space inside the fuselage now. We can put more stuff in it. And so inside the fuselage where you are, there might be a janitrol heater. It's burning avgas inside the fuselage with you. So with that, does it sound somewhat unsafe? Well, yeah, you're burning avgas inside the fuselage with you, but it has its own set of inspection criteria and its own set of regulations that manage its maintenance. So know where they are and know how to use them. Usually when these things go bad, it's because people use them wrong. Like the blower has to get turned on before the combustion starts. They burn fuel from somewhere, so you need to know which tank the combustion heater burns fuel from, so you know which tank to watch more closely so you don't run out. And they're pretty awesome. I mean, this little janitrol heater puts out 32,000 BTUs of heat, so that's like 3 RV heaters. So they work pretty well. They're really nice to have, especially if you're flying twin engine aircraft at higher altitudes for longer flights, where it's really colder, and they're really nice to have. Just gotta know how to use them. Another great thing is that nose baggage compartment. Okay, so here's another Piper Seneca 5. I think that's what we were looking at before too. Pretty sweet aircraft. Well, since there's no engine out here, all there is just the bay where the nose landing gear comes up into. Well, what are you going to do with that? Well, put stuff in it. It makes your weight and balance a lot more critical and a lot more important. And then the other stuff that comes is you notice what's right next to it? Propellers. Propellers that spin very fast on takeoff. I tell you what, if you have a nose baggage door, you need to check that sucker so many times before takeoff, because the last thing you want is to have that nose baggage door pop open in flight or on takeoff or anytime that engine's running. So you have a lot more places to put a lot more cargo, but you have to make sure that weight and balance is even more important, and you have to triple check and make sure that thing is locked and it's not going to pop open on you. Okay, so let's talk a little bit more about what you can do and other responsibilities that you have to follow now as a very professional multi-engine pilot. The accelerate stop distance is something you probably didn't see in the POH, either one of these in your single engine aircraft. So accelerate stop distance is the distance that it takes to go from a standstill, experience an engine failure during takeoff, and then go all the way to a stop again. It's important because you want to have runways longer than your accelerate stop distance. That way, if you have an engine failure, you can still get it stopped on the runway. You don't see these in your single engines because it kind of doesn't matter. If you have an engine failure, you're not taking off and you're not going anywhere. So, but in some multi-engine aircraft, you might have an accelerate go distance published in the POH. That's where it takes you to go from a standstill to takeoff, to start your takeoff roll, have an engine failure at VR, your rotation speed, or your VLOF. This is the liftoff speed. If there is a liftoff speed, most light twins don't have that. And then climb to 50-foot obstacle distance. That accelerate go distance is generally going to be a lot more because the aircraft had experienced an engine failure during takeoff and kept taking off. There are times where that's a good idea, and there's times where that is a bad idea, okay? And we'll talk a lot more about that. So accelerate stop distance, go from brake release, have an engine failure, stop. Accelerate go distance, go from brake release, have an engine failure, keep going. And newer, better graphics from the new Airplane Flying Handbook, newer Airplane Flying Handbook. And so you've got this area of decision, like, well, if you have an engine failure. So again, in a single engine airplane, it's easy. You have an engine failure, you're landing. You're landing straight ahead probably, or minimal turns, However, in a multi-engine aircraft, you have a lot more options. You have to decide every time before you take off when you can abort the takeoff, when you can continue your takeoff. And I got a nice little video that'll help with that one. As a general rule, though, you remember you retract the landing gear when there's no runway remaining for landing anymore, and you have a positive rate of climb. Well, in a multi-engine aircraft, it's going to be the exact same thing. When you can't land on the runway anymore, you raise the landing gear. So it's easy. If the gear's down, that means you can land on the runway. If an engine quits, land on the runway. And if the gear's up, that means you've taken the gear up because you can't land on the runway. You're probably going climbing and probably going flying on one engine. Okay, so more terminology we're talking about. So climb gradient, that's the angle that you climb. Okay, so a 1.5% climb gradient would be like you climbing at half the steepness of a normal glide slope. It's not very much, as opposed to rate of climb. Okay, rate of climb is how many feet per minute vertically that you're actually climbing. Climb gradient, it varies with forward speed as well as vertical speed. So here is out of I'm going to say a Piper Seneca with one engine inoperative, and they give you other steps for how it is. It changes with the gross weight, but you see what our rate of climb in feet per minute is. So on this aircraft, if we're at max gross weight and we are at 6,500 feet, we have 0 feet per minute climb. So if this aircraft is at max gross weight, if you have an engine failure, 6,500 feet is the highest you will get. Not only that, but if you were at a higher altitude, it will start sinking down to its 6,500 feet. And so single engine service ceiling, just like in your what we talked about before with the single engine aircraft, a single engine service ceiling is when you have one engine inoperative and you can still maintain 50 feet per minute. We probably also have a single engine absolute ceiling when you can't climb at all anymore. So you can pretty much plan on climbing to your single engine service ceiling if your engine's working well and you got all the bugs off your airplane, like the physical bugs anyway. But if you have an engine failure occur above that altitude, you're probably going to drop down to at least your single engine absolute ceiling, and then probably more, because honestly, one little gust of wind or a passenger moving around is going to make you descend, and then it's hard to get that altitude back again. As opposed to the all engine service ceiling. Okay, so with all engines working, how high it can go and maintain 100 feet per minute with climb. Single engine service ceiling is only 50 feet per minute. All engine service ceiling is 100 feet per minute rate of climb. And then absolute is when you can't go absolutely higher any longer. And so we got for instance, our PA-34 Seneca. Let's say we're at max gross weight with one engine inoperative. We can only go about 6,500 feet. Max gross weight with all engines operative looks like we can get to 16,000 feet. So you might be cruising along at 16,000 feet. One engine quits, you're going to slowly start working your way back down to 6,000 feet. Now let's talk about some procedural stuff. All right, don't be overwhelmed. A multi-engine airplane is just a big single-engine airplane. It just has more parts. So look, the pre-flight is going to be done the same way. There's a lot of stuff that's done the same way. All right. Taxiing's done the same way, but now you have more options. They're usually bigger. They usually take more room to turn around. And then because there's two engines, generally, if you're not careful and you have too much power on one than the other, people have a tendency to drag the brake, to just ride one brake to keep the aircraft from nosing right or left. Don't do that, okay? Pull the power back. You have two engines that are idling, which is making you want to go faster. So don't be afraid to pull the power back, and don't be afraid to use differential power. That means having one power on one engine more than the other to help you turn. Now, with that, we should always turn in this order. Turn should be made using a rudder pedal motion, and then differential power, and then differential braking. So if you want to turn the nose left, push the left pedal. If you need to turn a little sharper, put power in the right engine. If you still need to turn sharper, then you can also use differential braking. It's a little harder on the nose wheel, and then you're just beating up tires for nothing. And then just remember, cowl flaps need to be fully open when we're on the ground. You're probably flying faster and more power for our aircraft, and heat becomes the enemy with that. So make sure those cowl flaps are fully open. Coming in to land, it's pretty much the same thing, except you really need to plan your descent a whole lot better now. You're probably flying faster, you're probably flying higher, you're probably flying farther, which means you have less time to lose more altitude before you get to the airport. So you really just have to plan ahead. I mean, if you're doing 180 knots, you're doing 3 miles a minute. If you have to come down 10,000 feet, I like 3 minutes per 1,000 feet because it's easier on my ears, which means I'm going to have to descend for 30 minutes, and 30 minutes at 3 miles a minute is 90 miles away. So you're flying a multi-engine aircraft, and you're 90 miles from your destination. You have to start your descent. That's probably farther than you flew to become a private pilot in the first place. So you really got to plan ahead. I can't say that enough times. Put the gear down when you need to put the gear down, but you're flying a multi-engine airplane. You look cool. It's fast. It costs a lot of money. You probably don't want to put it down too soon. Some small differences when you're coming into flare. When you pull the power back to idle, both wings lose a little bit of lift, and then both propellers make more drag. So they generally slow down and land more abruptly. Because of that, full stall landings are generally undesirable in twins because they might stall more abruptly. So I know in multi-engine or in single-engine aircraft, we're probably start out teaching you to do full stall landings in a 172, or a PA-28, but that needs to start going away when you start flying more high-performance stuff and definitely multi-engine stuff. So you still land main wheels first. You still want to keep the nose wheel off the ground for as long as you can during that. See, that's under favorable wind conditions and runway conditions, the nose wheel can be held off for best aerodynamic braking. They want you to land on the mains and keep the nose wheel in the air, and that will slow the aircraft down. Continued elevator back pressure greatly assists the wheel brakes in stopping the airplane. So by you holding the nose wheel up, it's pushing the wheels down into the runway, which makes the brakes work better for when you do need them. So I always kind of say it this way, you will land a multi-engine aircraft on the mains with just a little bit of life left in those wings. So you almost fly it down onto the runway. Just again, it needs to be really close to a stall. That nose wheel needs to be off the ground, and then just keep it there. And let's see. If runway length is critical or if there's a strong crosswind, they say you should not rely solely on aerodynamic braking. Okay, so aerodynamic braking is a best way for you to slow that airplane down because you don't need brakes. You're using all the wind hitting your airplane. That's what you want. The reason I have this on here is they're saying that, when you're on the ground, elevator back pressure keeps the main wheels on the ground, adds more drag. And they say when necessary, you can retract the flaps, which puts more weight on the ground. However, they're saying right after they say you could do it, they say you shouldn't do it because it should not be accomplished as routine with each landing. I've seen way too many pilots out there. It's almost like a game to see how fast they can get the flaps up. The argument is they want to spoil the lift and put more weight on the wheels. Well, the problem is the flaps gave you drag, which was slowing you down. So I would much rather you do what all the books ask you to do, which is land on the mains, keep the nose wheel up, which puts more weight down on the wheels, and which allows for more effective braking. And the flaps are also providing drag, which all helps slow you down. Yes, some POHs talk about raising the flaps for better braking. And in my experience, you will get 10 times better landing performance if you stop messing around with the flaps and use back elevator and maximum braking. Again, when you need to. You shouldn't be using the brakes on most landings because you are using aerodynamic braking and you just use a little bit more runway so you don't have to ruin tires and brakes and all that other stuff. Let's see, coming to land, this is out of another, I think most of these are out of the Piper PA-34. That's what I got my multi-engine commercial rating in. So I think some of you will as well. And just follow the checklist. There's all the same stuff is in there, right? Cowl flaps we've talked about, fuel pumps, and the only difference is it's propellers instead of propeller, or it's mixtures and flaps, right? Just kidding. There's already more than one flap. Now over the landing gear, since there's an engine out there on the wing, there's usually a pretty handy place to put a mirror so you can see all your wheels. Even if you have a low-wing aircraft, you can generally have mirrors available to see them all. And you might see much higher flap speeds. Okay, so this aircraft has 3 different flap extension speeds. Only one of these is the VFE speed. It's the slowest one because you can have flaps fully extended at 125, but partial flaps much higher than that. And we've got our landing gear VLO speed is 150 in this aircraft. I pretty much already talked about that. I don't want to have to beat it up too much more. Go around is just like it was in a single engine airplane, but now you got 2 engines to worry about. Generally, what we're going to try to make automatic for you is whenever you do a go around, you go mixture forward, prop forward, then throttle forward. It's really tough when you go from your single engine, throttle only aircraft, and you start doing go arounds and more complex aircraft. But it's very important that you do your mixture and your prop first before you do the throttle, to make sure that you're in the right gear if you want to think about that for doing a go around. And of course, the thing is, make a timely decision. So earlier is better if you're going to do a go around. So it'd be max power, and then flaps partially retracted, positive climb, gear up, gain some airspeed, take out some flaps, gain some airspeed, take out some flaps. All right, so that's it for the first half of this discussion. Is multi-engine systems, a few more terminologies, and operational, what to do when both engines work. And the whole second half of this video is going to talk about what to do when things go bump in the night. This is the hard part about multi-engine training, is dealing with that inevitable engine failure. Remember I said, if you got 4 engines, you just quadrupled your chances for an engine failure. So did it really make it more safe? Yes, it's up to you though. This is a picture of an A380, I think an Air France A380. Let's see, is it Air France? Yeah. That had a number 4 engine uncontained failure, and it just blew part of the engine off. It actually damaged the pylon and the mount and all kinds of stuff on there. They had to divert and land, I think, Goose Bay, Canada, and they had to ferry all their 500 or something passengers off to another location and then get them a new aircraft, and then they had to work on fixing this. It ended up damaging the pylon, so they had to, I think, fly it out to get it repaired somewhere. But yeah, you're like, well, they got 3 other engines. What's the big deal? Well, it was also the outboard engine. So when it failed, it had the most amount of yawing in that direction. And then obviously parts of it were missing, and it just caused a whole bunch of drag out there. So this is actually a separate lesson in the Jeppesen commercial syllabus. Again, I'm not asking you to go buy that green multi-engine book. We're still using information from the Airplane Flying Handbook, Chapter 12, and then some good videos that are credited later on, and especially some bold method ones that we're going to watch right now. So some of these will be linked down below, and these videos are good enough that we're going to watch them together.
When I'm flying the Cirrus under Part 91, or pretty much any other airplane under 91, the FAA really doesn't have much to say about runway length. FAR 91.103, pre-flight action, that requires us to determine the runway lengths and takeoff and landing distances, but it doesn't require us to have any padding. In fact, unless you're flying a large or transport category aircraft, FAR Part 91 never directly says that the runway has to be long enough to meet your takeoff distance, though that's really covered by the catch-all 91.13, careless or reckless operation. But if you're flying under Part 121, the rules, they're much more limiting. Your runway length and the associated maximum takeoff weight is governed by the FAR takeoff field length. It computes the distance to make a normal all-engine takeoff, and it considers the distance to reject a takeoff as well as continue after an engine failure. And then you limit your weight to make sure that all three can safely happen on the runway. It's not the only weight limiting calculation done in Part 121 pre-flight planning, but it's a pretty key ingredient. So we'll take a look at how field length limits the takeoff weight, starting with an all-engine takeoff. The all-engine takeoff distance is the total length to accelerate from a full stop on all engines, rotate at VR, and climb out to reach 35 feet at an airspeed that is at least V2, your takeoff safety speed. The FARs require 115% of that value, and that's called the all-engine takeoff field length. Your takeoff run, the portion before liftoff, has to occur within the runway's length. However, you can use a clearway during climb out to 35 feet. A clearway is an area off the departure end of the runway, 500 feet wide, that slopes up at 1.25%. Obstacles except for certain threshold lights cannot penetrate the clearway. If an airline includes a clearway when evaluating the takeoff, it can't be longer than one half of the runway's length. Well, the FAA allows you to use a clearway during your takeoff planning. Not all of the airlines choose to use it. Okay, so we've looked at the all-engine takeoff and the FAR field length, but it also looks at an engine failure. One where you stop and one where you go. And that brings us to accelerate stop and accelerate go distances. And V1, the point where you switch from stopping to going. You can think of it as a takeoff action speed. V1 is the fastest speed where the pilot must take the first action to reject a takeoff so that the aircraft will come to a stop within the calculated accelerate stop distance. That might mean applying brakes, reducing thrust, or deploying speed brakes. V1's also the minimum speed during a takeoff where, following the failure of the critical engine, the pilot can continue the takeoff and reach 35 feet above the takeoff surface at V2 airspeed, within the computed accelerate go distance. You might hear V1 called the takeoff decision speed, but that's actually pretty misleading. Your decision needs to be made before V1 so that you take the right action if an engine fails at V1. If you try to reject a takeoff after V1 and you're heavy, you could easily run out of concrete. So airlines and pilots develop specific procedures to make sure that they always take the right action when they're close to V1. More on that in a bit. But first, let's take a look at those distances in more detail. And we'll start with the accelerate stop distance. This is the total distance to accelerate the aircraft from a standing start to V1, have the critical engine fail just prior to V1, take the first action to stop the aircraft at V1, and then bring the aircraft to a full stop. The certification rules for accelerate stop distance have changed over the years, but in general, when they certify a Part 25 transport aircraft, the engine fails about 1 second before V1. And during certification, the distance is calculated without using reverse thrust, only wheel braking and speed brakes. Some aircraft actually are allowed to use reverse thrust to certify wet runway accelerate stop distance under an amendment to FAR Part 25. And of course, if you actually reject a takeoff and you have reverse thrust available, you can use it. FAR Part 121 requires a runway long enough to meet the accelerate stop distance for your weight at V1. You can include a stopway, a hard surface portion after the runway intended for rollout during a rejected takeoff, and that surface can't structurally damage the aircraft. Well, the FAA allows you to include a stopway when you're computing accelerate stop distance. Not all airlines choose to use it. Okay, accelerate go. That looks at the opposite situation. You lose an engine at V engine failure, VEF, just prior to V1, and you continue the takeoff. This is the total distance to accelerate from a standing start through the engine failure and V1 and continue the takeoff to 35 feet at your takeoff safety speed, V2, using only aerodynamic controls and average piloting skills. While the FAA allows you to include a clearway when computing accelerate go performance, not all airlines choose to use it. V1 is usually positioned so that the accelerate go and accelerate stop distances are the same. This is called a balanced field, and it allows you to take off with the most weight possible for a specific runway length. As V1 gets faster, it takes less energy and distance to continue takeoff, reach V2, and 35 feet after an engine failure. So as you increase V1, you can meet accelerate go requirements for a runway at a higher gross weight. But as you increase V1, it takes more distance and energy to stop following a failure. So as you increase V1, you must be lighter to meet the accelerate stop requirements for the runway. The point where these lines meet is the balanced field limit V1 speed, and This weight is called the balanced field limit weight. That V1 speed allows you to take off with the most weight on a specific runway. Of course, you usually take off lighter than the balanced field limit weight, so for takeoff, V1 is balanced at your actual weight. It's often computed off-site, and it's sent to your aircraft via ACARS. So, your takeoff weight is limited by the longest of these three, all-engine takeoff field length, and the accelerate stop or accelerate go lengths. For most twin-engine aircraft, accelerate stop or go is the longest factor, because they lose half of their thrust after an engine failure. For four-engine aircraft, the all-engine takeoff field length is often the limiting factor because they only lose 1/4 of their thrust after a failure. And three-engine aircraft, like a Falcon jet, might be limited by the accelerate stop or go distance as well. There's another rule which might affect V1, and that's that V1 cannot be faster than rotation speed, VR. If it is, V1's adjusted so that it equals VR, and this is more common in three-engine aircraft than two, but you can find it in both. Okay, earlier we said that airlines develop specific procedures to make sure that crews don't reject a takeoff after V1, and they do this with a number of tactics. On a Republic E-175, the pilot monitoring calls V1 5 knots ahead of the V1 speed. Since the aircraft normally accelerates at a rate of about 5 knots a second, that puts the V1 call 1 second before the actual speed, and by the time the pilot hears and recognizes it, the aircraft has actually reached V1 speed. And on a Republic E-175, the captain removes their hand from the thrust levers once they hear the V1 call. That way, if something fails after V1, they don't try to reject a takeoff. Okay, let's take a look at these procedures as we depart Indy.
Delta 329, fly runway heading runway 23 right, clear for takeoff.
Fly runway heading runway 23 right, clear for takeoff, Delta 329.
Brickyard 722, Indy Tower, runway 23 right, line up and wait.
23 right, line up and wait, Brickyard 722.
Delta 2196, Indy Tower,
line up and
runway 23
wait.
right, continue traffic holding in position. Continue, Delta 2196.
B4, takeoff.
Takeoff, okay.
For takeoff, checklist, min fuel, verify.
American
4.8
1296,
required,
contact departure,
15.4 on board.
48 required, 15-4 on board.
Flight attendants notified, transponder TARA, takeoff configuration checked, runway verified, 23 right.
23 right.
For takeoff, checklist complete.
Thank you.
Brickyard 722, wind 0605, runway 23 right, clear for takeoff.
23 right, clear for takeoff, Brickyard 722.
You have the controls.
My controls.
Delta
Toga.
329, contact departure, good day.
Departure Delta 329. Toga set. $80 knots.
Checked.
B1. Rotate. Positive rate.
Gear up.
Gear up.
Delta 2196, runway 23 right, clear to land. Clear to land 23 right, Delta 2196.
Heading. VNAV.
Brickyard 722, turn left heading 215, contact departure, good morning.
215, take care, Brickyard 722.
Heading 215.
It's 215.
Flaps 1.
Plus 1.
Flaps up after takeoff checklist.
Flaps up.
Good morning, departure, Brickyard 722 is out of 3,000, climbing 5,000.
Brickyard 722, Indy departure, radar contact, climb maintain 12,000, turn left, direct Sneva.
Up to 12,000, direct Sneva, Brickyard 722.
2000 set.
12,000 set.
That's a normal takeoff. Let's take a look at a rejected takeoff as we accelerate towards V1.
Toga. Toga set. Knots.
Check. Reject.
To reverse. Knots. Knots.
Okay, normal takeoff and even a rejected takeoff, they both seem pretty routine. And while rejecting a takeoff isn't very common, the procedures centered around V1 make the process really simple because your decision's already been made before anything happens.
All right. So it's linked down below in case you want to watch it again. You don't have to go all the way through my video to check that out. Thanks to Alex and all the folks over there at Bold Method for sharing that with us. And I'll probably link you to their webpage that has that video on it because there's a whole lot of other good information on that as well. Talking about briefing the takeoff. Having 70% of your speed by 50% of the runway, and then there's that video down at the bottom.
When I'm flying the Cirrus...
Okay, so we're talking about emergencies here, right? So what we just saw was a Part 121 aircraft with a accelerate go capability. You may not always have that. So in your light twin aircraft specifically, like the Piper Seneca doesn't even have an accelerate go chart on the older, less powered versions anyway, because if your engine quits, they don't want you trying to climb out of one engine. The BE-76 does, even though it has less powerful engines, but it's also lighter, but it takes you something like miles to climb 50 feet. Okay, so the chart's there, but so in a light twin aircraft, there's a pretty good chance that you're going, a serious option for you would still be to land, even if it means going off the end of the runway and going off airport. And that's as we're seeing here now. We had an engine failure on takeoff. We decided that our best course of action is going to be to put it down, even if it means overrunning the end of the runway. A large transport category aircraft, you've already made the decision to continue flying even when you're still on the ground if you have an engine failure. But in your light twin aircraft, there's still always the option that you might want to pull both throttles back to idle and just land somewhere straight ahead somewhere, even if it's off airport. So this is kind of a recap of the video. So when do you reject and when do you don't? Well, that's if you have a published V1 speed, that is the speed you use. Engine failure before V1, abort. Engine failure after V1, go. And that's pretty cut and dry there. There's very few times where you would want to go against that. Then the V2, they mentioned in the video, that's your takeoff safety speed. That's when you can safely climb with one engine operative. So you can get in the air with one engine, but V2 is when you've now successfully began your climb. And then of course we know VR, that's when you begin rotating the aircraft prior to liftoff. So I put that on here because VR is rotate speed, that's when you begin to rotate. VR is not like liftoff speed, VLOF. You do not get airborne at VR. At VR is when you start rotating the aircraft to take off. And video did a good job with accelerate stop and accelerate go. Here's the long wordy definitions of these V speeds. And you can go ahead and pause this and read it through them if you want. Otherwise, I think we've gone over it enough times already. So here's an NTSB report. All right, as you see here, it was the University of Michigan's men's basketball team. They aborted to take off after V1. And this is what happens when you abort a takeoff after V1. There was bad weather the night before. They started the takeoff, and everything basically says the pilot executed a rejected takeoff. You see significant damage, and one person got minor injuries, but hey, could have been a whole lot worse, right? And so from the video just watched, said, well, that was stupid. Why did they aborted their takeoff too late, or they didn't do their balance field length and all the other flight planning that goes into it. Well, turns out this pilot did the exact right thing, because the NTSB report came out, and there was the crazy windstorm that happened at the field the night before had damaged the stabilator, and when the pilot went to rotate, he knew something felt wrong and aborted the takeoff, even though he was after V1. And saved everybody on the aircraft as a result. So had he tried to fly, then he would not have been able to. Okay, so V1's really easy. If you have V1 and it was an engine failure, it's abort before it, go flying after it. However, if it's not an engine failure, you still should have the option and ability to abort for a lot of other reasons, especially a flight control problem. So anyway, that pilot's a hero because they actually saved everybody on board. Let's just show some examples of different V speeds and performance numbers. Here's a Piper Seneca, a couple different gross weights. You've got your different best rate of climb speeds, and your single engine best rate of climb speeds, and you got your VMCs and your ceilings, and I don't remember why else this is on here. Basically to let you know that you need to learn your aircraft. Okay, so we already saw these videos. Engine failure during a takeoff. This is out of the one of those light twin aircraft. They're saying if you haven't got at least 100 miles per hour of calibrated airspeed, close both throttles immediately and stop straight ahead. If you can't get stopped before the runway runs out, they don't say take off. They say go ahead and start closing things off and minimizing your chances of post-crash fire. Okay, so this POH says if you're less than 100 knots, you're not taking off, so can't abort the takeoff. Pretty cut and dry. So in this aircraft, 100 miles per hour, I keep saying knots, but 100 miles per hour is your takeoff decision speed. And here's what it would look like. Here's an A330. We're watching this with the zoom lens from a really far ways away, so the sound is extremely delayed from the aircraft. An A330 on takeoff, you're going to see an engine failure right before V1. Okay, so there it goes. You see immediately the aircraft yaw towards that dead engine. There's the boom. Now they're aborting the takeoff. Both thrust reversers came on, spoilers come up, and they got on the brakes, and they got this thing stopped very quickly. And they sit there and make some radio calls.
Understood, sir. They're on the way now.
Rescue comes out, and this way they can see if they need to evacuate anybody on the field, or if they need to put out fires or anything like that. But it was pretty much self-contained engine failure. So let's go ahead and see this part of it again. So everything was fine, and then they had the engine failure. And already this thing is yawing towards that dead engine. And you see pretty much what looks like full left rudder went on there to keep the aircraft from yawing that direction. And we're trained in the multi-engine world that as soon as this happens, every throttle you can grab comes back, because you're really trying to keep this engine from driving you off that end of the runway. So already they're pulling the throttles back, and then in these they just keep pulling them back, and that puts on the thrust reversers. And then there might be automatic braking, where they're getting on the brakes right now. So spoilers are spoiling lift, put more weight on the wheels. The wheels are using braking, and they're using reverse thrust to get it slowed down. So if you're going to have an engine failure before we have V1, this is what it should look like. Okay, and then the same POH says if you have got 100 miles per hour, if you can land, they still want you to land. It's in big capital letters. They're saying if you've already got 100 miles per hour and you're already in the air, but your gear is still down, you need to pull the throttles back to idle and land straight ahead. All right, you're going to use the overrun area. You're probably going to damage the aircraft. But look, the POH says, I don't care even if you're in the air, but the gear is still down, you need to close both throttles and land somewhere straight ahead. And then they're saying right here is this is the only gray area. Is like, if it's inadequate for stopping, you have to decide whether to abort the takeoff or to continue. And you need to make this decision before you're going down the runway and the engine is failing on you. So you need to have decided with density, altitude, loading. This is part of your pre-takeoff briefing. It's very, very important in multi-engine aircraft. Now here's what it's going to look like in the inside if you continue a takeoff with an engine failure.
Hey folks, we're on a Cessna Citation, getting ready to take off on runway 13 at Falcon Field. Some of you guys here on Facebook wanted to see a V1 cut, what that looks like, so Captain Mike here is going to do a V1 cut. Our speeds today, our V2 is 97, and our fan speed is 97.4, so we're going to go ahead and get a V1 cut in here at Falcon Field. We'll climb to 400 feet, level off, flaps retract, and climb out at 152 as our Wiener. You guys ready? What do you say, Captain Mike? You ready?
Yeah, let's do it.
All right.
All right.
Stop. Field traffic 122 Whiskey Sierra, departing 13 Falcon.
Set power.
Power set. V1. Rotate.
Okay, you got positive.
Positive rate.
Yep.
Good. Now nose up a little bit more. Fly that V2.
Yep.
There you go.
Correcting.
Looks good. There's 400 feet.
Okay, 400. Pitch down. Looking for meter. Okay, flaps approach.
Flaps up.
Flaps up after takeoff check.
Takeoff check was complete. There's 152, Captain.
Climbing.
And one more checklist.
And let me get an engine shutdown check, please.
All right, that's all complete. After takeoff checklist, I'm going to give you the other throttle. Nice job.
Okay, so we see a lot of the similarities. We see how in this one, Toga, you saw in the other video, is takeoff, go around power. So he sets the power, then he's staying there because either he would pull the throttles back to abort the takeoff at V1, but right here you see him simulating an engine failure right after V1. It says V1 and rotate, and then right then he starts pulling the engine back. But they've already said V1. They've already passed their takeoff decision speed, so they're going to go fly. This aircraft has more than enough climb performance. They can take off and climb away, even with that one engine inoperative. You see how it was the right engine that quit, and so the aircraft keeps trying to yaw and roll towards the right, so this pilot has a lot of left aileron in and probably a whole lot of left rudder in as well to overcome those forces. And then just, it's another day. Continue doing what you're doing. So that's why we train. Okay, and this is, I think, what we just saw in the other one. It's up to you. So you need to make the decision before you take off. Before you start your takeoff roll, when you're going to abort and when you're going to continue your takeoff. Okay, so let's talk a little bit more about the critical engine. The engine failure whose failure most adversely affects controllability and performance if it were to fail. And the four factors that determine our critical engine are PAST, because we love acronyms, all right? So it's P factor, accelerated strip seam, spiraling, slipstream, and torque. They sound like our left turning tendencies, and then you know what? You're not too far off. Okay, so let's say if we did not have counter-rotating propellers, and let's say they both turned the traditional way. You accidentally put the wrong engine on this Beach Duchess. You'd have four left turning tendencies for both engines. You'd have P factor, that's the increased thrust on the downward blade as opposed to the upward blade. And both engines would have that. And the problem is the right engine has a longer arm on its more P factor. So this engine causes more left turning tendencies than this one. So just for that factor alone, that makes this the critical engine because it is going to be harder to handle the aircraft. Accelerated slipstream, that is as the propeller blows air over the wing, it's creating lift. And so if you lose the slipstream, you lose lift on that wing. And a little bit of P factor, this one's making a little bit more lift on the outboard portion there. Spiraling slipstream. So as just like the spiraling slipstream makes left turning tendencies in your single engine aircraft, if they both rotate this direction, then you end up with force on the tail, which would cause it to turn left in this instance here, as opposed to forces that don't go on that tail surface, which would be countered by counter-rotating propellers, but I'll kind of diagram that in a second. And then, of course, torque. If both engines are turning clockwise as you view them from behind, then both engines are trying to make the aircraft turn counterclockwise because of Newton's third law. Every action has an equal and opposite reaction. So propellers and crankshafts go right, aircraft goes left. Now, with that, if the left engine were to fail, you would actually want to raise the right engine and bank towards the good engine. But torque is actually making you go farther left. So if the right engine were to fail, you would want to raise the right engine, and torque would make that happen. So if you have both same direction propellers, these are the four factors that make the left engine the critical engine. Let's go back to here so I don't have to redo it all. Now with counter-rotating propellers, these are all offset. P factor is greatest on the inboard portion of both blades. So it's not out here with a larger arm. So P factor is not only less, but it's equal on one engine versus the other. Accelerated slipstream is the same on one engine versus the other. Spiraling slipstream will have the same effect on one engine versus the other. And then torque will have the exact same effect, and not only that, but now torque will raise the dead engine, which is what you want to happen. So the torque from the operating engine will raise the dead engine and will bank it towards the good engine. These are all good things. So the way, the critical engine in a normal operating aircraft and clockwise from the rear would be the left engine, but most of your light twins would be like that. Then again, most of your light twins are counter-rotating. So you can either consider that neither engine is critical or both engines are critical, because we already said this is probably not going to climb on one engine. So technically it doesn't have a critical engine because they're counter-rotating. Technically they're both very critical to your flight. Okay, so what happens when you're flying along and the engine quits? So if you have any kind of an uncommanded roll or an uncommanded yaw, like you saw in the takeoff video, or like you were watching them do in the video after the engine failure after V1, most important thing for you to do is maintain control of your aircraft. That's always, stay calm and fly the airplane, right? So what we do is we have this kind of mantra. We go maintain control, power up, clean up, identify, verify, and then on the next page. So what I mean by that is maintain control. You do what you got to do to make the airplane do what you want it to. Maintain your blue line speed. I'm not talking about takeoff, V1, V2, you're way below that, but maintain your blue line speed. Power up. Go from right to left, push the mixtures forward, push the props forward, push the throttles forward. Assuming you maybe had, pulled back some for takeoff climb settings. And you notice it says throttles. You don't just push the good engine forward because you don't know which engine is not working yet. So you push all your throttles forward. Cleanup. You have to gear up, flaps up, to get the gear up because you don't want the drag, flaps up because you don't want the drag. Identify. You actually straight up see which foot you're not using right now because you have so much rudder pressure on the good engine. So we have this mantra, dead foot, dead engine. So I usually take it all the way off and I tap it on the ground. Then I'll say, okay, left foot, dead foot, left engine, dead engine. And then I verify. And the way you do that is you put your hand on the suspected dead engine. And if you have a co-pilot, they would usually say engine verified or something like that. You look outside the aircraft through your instruments and you pull back that throttle. And if the engine was already dead, nothing should change. If the aircraft yaws or rolls, then that engine still had power on it, which means you pulled back the wrong one. And then depends on your altitude. The way in light twins, the way I brief it is if I'm below 3,000 feet, we're going to feather that engine, we're going to divert to a new landing spot, and we're going to declare an emergency. And if I'm above 3,000 feet above ground level, I'm going to troubleshoot first. I'm going to check with fuel, carb heat, mixture, fuel pumps, alternate air, magnetos. The theory is I have enough altitude now that even if I can't maintain altitude, I have enough time to troubleshoot first. And then if I cannot get it fixed, then I'm going to feather the engine, divert, and declare an emergency. So I straight up have the kind of the talk. Where's it at here? So engine failure occurs on a maintain control. I'm going to power up. I'm going to clean up, gear up, flaps up, identify dead foot, dead engine. I'm going to verify with the throttle looking for change in altitude. Below 3,000 feet, I'm going to feather, divert, declare. Above 3,000 feet, first I'm going to try to troubleshoot. If I can't get it running, then I'm going to feather, divert, declare. When you get your multi-engine, you're going to do your kind of multi-engine takeoff briefing, hundreds of times. So you're going to get pretty good at it pretty quick. Okay, a little bit more about VMC. There's the regulation actually that has since changed. I need to put the new regulation on there. So if you look for 23.149, you won't find it. It's a 4-digit number now. Just search for VMC and you'll find it, the new regulation. Is the airspeed which, when the critical engine is suddenly made inoperative, it's possible to maintain control of the aircraft without getting the engine working again. And here's all the situations for it. And basically everything as bad as possible. So here's a nice handy chart for us. Thank you, pilotscafe.com, for providing this one for us. And demonstrated VMC is what they did. An actual VMC might be a little bit higher than that, or a little bit lower, than that. And here's just a handy chart. Okay, so if you go up in density altitude, the engines make less power, so you have less asymmetrical thrust, which is good because you can go slower then because your engine makes less power without losing control. However, obviously that hurts your performance because your engine is not making as much power. You get heavier, it actually helps your VMC, but it also hurts your performance. You won't climb as well on one engine. Windmilling, I'm going to come back to windmilling prop. Aft CG actually hurts your VMC because it minimizes your rudder arm, and your rudder becomes less effective when your CG moves to the aft, but hey, it helps your performance. Flaps, they slow down your VMC, which is bad, and they hurt your performance, which is bad. They help your VMC. You can go slower without stalling, but obviously you don't climb as well with all that drag out there. Gear being extended actually helps your VMC, but gear being extended hurts your performance. Gear being up hurts your VMC, but it helps your performance. And then so the only and the windmilling propeller is the only thing that's really bad and really bad. Is that windmilling propeller increases your VMC because it makes more drag on one side of the aircraft, and it riggedy wrecks your performance because it's causing so much drag. So the worst thing you could do is have a windmill propeller. The best thing you can do is bank towards your good engine. Remember, you raise the dead engine. You raise that dead engine and you bank up to 5 degrees towards your good engine. When you're doing that, what you're doing is you're using some of your horizontal lift to offset the side slip that's induced from having that engine failure. What happens if you go below VMC? This. Okay, this aircraft's always having some motor problems. Doesn't sound like it's doing very well. One engine's trying pretty hard. They look like they're going pretty slow. You see the aircraft banking to the left now. They're probably not trying to turn left. What's happening is they got slow enough to where even the right aileron they were putting in wasn't enough to keep it from rolling towards the left. And see, they've definitely lost control of it now. If this happens to you, what you're going to be trained with your VMC demo is you just pull the power back. I'm sure you're going to descend, but that's better than the alternative we're just about to see here. What gets pilots in trouble on multi-engine aircraft is when they refuse to accept the fact that they can't keep flying on one engine. And there's the VMC part of the roll. See how quickly it happened from I'm starting to lose directional control to what would be a pretty sweet roll if it didn't happen a few hundred feet above the ground. So don't be that guy. If you have an engine fails, fly blue line, never go below red line. And then if you do start to VMC roll, your only option at that point in time is to pull power back. All right, so once again, you're flying along on your engine quit, maintain control, power up, clean up, identify, verify, fix if you're high enough, or feather, divert, declare if you're not. Here is a couple different aircraft procedures for engine failures. They do the ABCs of an engine failure, right? Yeah, but they don't line up with ABC at all. A lot of the same stuff. Minimum speed, best rated climb speeds. You can do mixture prop throttles forward, gear up, flaps up, pump on. We're starting to troubleshoot now, right? And they identify the bad engine. We retard the throttle to verify that bad engine. We feather that bad engine. You then start shutting down that bad engine. You turn off the mixture, you trim it, bank 5 degrees towards that operating engine. I put that there because we just discussed that. And you start turning off the pump and off the magnetos, and you start closing the cowl flaps, and you start shutting down that bad engine. You might want to consider crossfeed because, again, you want to use the fuel that's in that dead wing. It says consider because why did that engine quit? If bad fuel made that engine quit, you don't want to put that fuel in the other engine too. So it's consider it. If you need to think of why the engine quit, try to do some troubleshooting that way. Here's the little picture on the why we do 5 degrees towards our good engine. If you go wings level, ball centered, the aircraft is actually side slipping through the air because of all that rudder force, and the aircraft is going through the air sideways. And we didn't figure this out until somebody stuck a yaw string out there and they realized when they were doing one engine out flight, the whole aircraft was flying sideways through the air. So it's a little bit better actually if you do a little bit of bank towards, you raise the dead engine, a little bit of bank towards the good engine, and you let just about a half a ball out. And when you do that, the aircraft flies a whole lot better. So if in case you don't have a string on the nose of your aircraft, you're going to mess around with it and you'll kind of see what feels better. This will increase your climb performance dramatically. So remember that zero side slip flight is what gives us the best increase in performance. It lowers our VMC and it raises our performance. Don't bank too much because then it starts slipping the other direction. Here's another VMC demo. Some of you might have heard about this, the TransAsia Flight 235. This ATR is a very high performance, very well equipped aircraft. In this example, what happened was there's an automatic feathering system in one engine. The aircraft took off. One of the engines feathered because it thought that it failed, but it was actually a bad torque sensor. And the pilot, out of habit, turned off the good engine. And this is just make sure that you train with both engines getting turned off because you don't want this to happen to you. We see clear here VMC roll right at the very end. And you see pretty much the luckiest car in the world because they survived. So you see them trying, holding off. Basically, they started getting power going back on one engine again. And it was a VMC roller, just a straight up stall. Okay, so in other words, practice with both engines. Practice failing both engines. When you have the engine out and you're coming back into land, it's just going to plan ahead a little better. Okay, the thing is you don't want to have to do a go around. So with one engine out, you may not be able to climb. So a go around may be impossible. So just plan ahead well enough. Of course, practice, but the biggest thing you do is don't put your gear down or your flaps down too soon. So don't do that until you know you've got the airport made. And if you're scared, don't be, all right? So back in the day, Bob Hoover here, I need another way to show this one. Bob Hoover started doing air shows Looks like it's not going to work for me in the video, so I will link to it down below. You are all going to want to go watch this video, trust me. He did some crazy stuff with a multi-engine airplane. He would feather one engine and do a bunch of aromatics, then he would feather both engines and do more aerobatics, and then he would land the aircraft dead stick midfield and taxi the parking and shut it down. Yeah, pretty much the best pilot there ever was. And if any pilot's offended by me saying that, then they obviously don't know the legend of Bob Hoover as well. So go ahead and watch this video and you'll see that you shouldn't be scared. I know I've just spent the last probably hour plus telling you about how multi-engine airplanes are going to kill you, but it all comes down to you need to know your system, you need to know your aircraft, and don't ask it to do things that it cannot do. So Bob Hoover does aerobatics in the twin-engine commuter aircraft. It's not even aerobatic like airshow aircraft. But because he understands what he can and cannot do with that aircraft, he doesn't ask it to do things that it can't do. So if you don't ask your aircraft to do what it can't, it's going to help you out a whole lot better. So I guess that is probably it for this video, folks. Check Canvas for any other assignments or any extra credit. This probably has a reading assignment, a video, and then a quiz, and probably another online course that you need to go take. So make sure you do that. And next week, double check, but it's probably going to be chapter 13, commercial considerations, and for following the Jefferson syllabus. And that's it. I could go through a couple questions right now, but I'm not going to waste your time with those. I want you to go back through and watch the video and look up these questions on your quiz. Look down below for links. Watch that Bob Hoover video. You guys will enjoy it. And thanks for watching. See you back on campus.